Oh, yes, another draft physics video production. Seems to keep happening. So anyway, not too much in the comments section, so yeah, a little bit boring. Voyager probe exits the heliosphere. Interesting results in plasma detection. Well, interesting to who? I mean, yes, there's radiation in the universe, cosmic rays, all kinds of stuff. But it's a tiny, 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 the visible stuff, the stuff we can detect, amount, in terms of it being atoms and nuclei and all that kind of stuff. Now, obviously, I'm arguing there's a ton of force that we can't see, but force doesn't matter. So, and plasma is little bits of matter, essentially. Um, so they're not really counting how much, I mean, you could just say interesting results in that it gets darker when you fly out of the solar system. Yes, it gets darker. And the stars might get brighter, because you're getting closer to them. It's so let's read more. So he has to put all this space in here for this article that's totally uninteresting. This is significant. No, it isn't, because it gives a clear understanding of interstellar space. No, it really doesn't. It really doesn't. There's nothing brilliantly surprising in any of this stuff. Yes, the entire solar system had a lot more crap in it, say 5 billion years ago. A lot more. And it's slowly but surely getting cleaner and cleaner and cleaner. And it's still in that process. So totally uninteresting. I mean, the planets that are left are not even a good representation of what was in the field to start with. And the fact that stuff gets into orbits is really it's a difficult process, and a whole bunch of stuff smashed into each other and all that kind of crap. So there's just nothing interesting in this subject. So people say the word plasma like it means something. Space is still a really, really strong vacuum. It means it doesn't have anything in it. Very little stuff is left. And so, you could have 10 times as much little amount and it would still be nothing. I mean, it's so next to nothing that even if you doubled it or tripled it or quadrupled it, or even times it 1,000, it still wouldn't add up to like a cupful per square mile. So this isn't interesting. What do you think's happening? What do you think? The magical plasma is controlling everything? There's gigantic waves of electricity flying through the almost non-existent plasma, the conductor that almost doesn't even exist at all. I mean, you want to say just what? Scary to believe, whatever that means. Ooh, how ominous. Ugh, just so irritating. They hype everything. Everything is hyped. That's why they're writing the article, is because they're trying to make it interesting. Not because it is. You haven't seen that concept, like every single snowstorm is like, it's the mega storm, it's the biggest, blah, blah, blah. All the hype. I don't think this new set of 2 plus 2 plus 2 rules can work. Well, you can think whatever you want. The point is get to something more elemental. At least try to start that way with processes where you don't have to say, well, it just magically does this or it just magically does that. So I'm just trying to get away from that and see if you can start from the crudest beginning and still make it work. And I think you can. Proton, electron, proton configurations in line can now trap force bits between 2 protons. Can now. What is that? Whatever that means. Just as the electron wasn't there. Right. So that's the price you pay, is you gain something and then you lose something. So the trick is going to be, the key is the neutron. What exactly is a neutron? How does it work? And blah, blah, blah. So you can come up with other scenarios, for the argument. So the idea is you have the 2 opposite things. Why am I drawing it there? Huh. Well, it doesn't really matter. It always comes out looking crooked. All right, two things that are the same, and then you put something in between. And the rule kind of was that this thing in between, mitigates the pressure that would exist between the two things that are the same. So we know same things repel. So the idea is the easiest way to make repulsion is just to put something between them and say, and it hits. Ping pong paddles scenario. I mean, you put the ball between and it bounces back and forth essentially, and this thing was the mitigator in the sense that these two things can't get close to each other, because the closer they get, the more impacts. And so if you put this in here and he was knocking that energy out of the system some way, then you can, because now you can get these things really close because this thing is getting rid of the ping pong balls. It's a way of getting rid of them. Well, you still can have that with a cruder system if you just understand that momentum, as you change the direction something's moving, you change its likelihood of changing that direction. So the more it moves, the more likely it is to change its direction, you could argue. So this little thing could just be moving. And then the other scenario is that this three-dimensional thing is sort of interesting. I mean, we don't even have, we can't even say for sure that these aren't two-dimensional objects. No one's really thought about it, I don't think. I mean, gave it much thought. But what if, protons and electrons only exist in two dimensions, and they're existing in two opposite dimensions, obviously. So like the electron would be in this and this dimension, and then the proton could be in, I just have to draw it different, this and this dimension, and this third dimension would be non-accessible. And then you can create all kinds of interesting scenarios in terms of how they would interact. It gets really complicated though, doing it in your head with three dimensions. I don't know if I need to really get rid of that. But the other thing is that the whole idea of this momentum thing, that you can't hit something going the same direction as you. So if there's a bit of force inside of something, and you bring a force in, well, it's not going to hit something going away from it the same speed. And so then you sort of narrowed your what you're going to hit to, the stuff going this way, and the stuff coming at you. And then in the three dimensions, you got the stuff going this way. And you have more stuff going back and forth in those two dimensions than you do have it going in this direction, clearly. I mean, an obvious difference. But you'd also have the idea that the faster you're going into this, the more of this you're going to hit. But theoretically, the more of this you're going to hit, and the more of this you're going to hit. But this is another concept that's a little difficult to think of in terms of thinking inside of your head. Like, what's the odds if something is bouncing back and forth this way, and something's bouncing back and forth this way, and you throw something random into the box, from this direction? Are you more likely to hit the thing going this way, or are you more likely to hit the thing going this way? It's an interesting question. I don't know the answer. If somebody does. You could just say it with ducks. Like if a duck is flying towards you, and there's a duck's flying this way across, which duck is easier to hit? If you're just randomly shot, which duck are you going to hit more often? The one going back and forth, or the one going back and forth this way? Interesting question. I think just because it has to do with this, how much space, how much time you're actually in the space is what you're really calculating. And you could almost argue that it's a center of gravity issue again. Like I said, if you had things orbiting, moving in orbits, that their center of gravity changes, and like this motion and this motion, you'd say theoretically those two have to have the same center of gravity. Just trying to think through it. See, it starts to occupy your whole conscious mind, and then you're stuck not being able to talk. So you can't talk and think at the same time. That's not too easy to do. It's a little bit challenging. So what point was I going to make? It has to do with that whole gravitational wave thing, when you have two things, swinging around each other, just orbiting each other. You do have this circumstance where, from a point of view, just trying to think through this thing, what changes? Yeah, I can't remember. There's something changes because of the distance between the two objects from a distance. Well, anyway, I won't even get into it because I can't remember what my point was. But like I said, there's a slight more likelihood because it's in the space more often in one dimension than the other, or something. Well, anyway, doesn't matter. Sorry, got distracted. So the point would be is that you're more likely to hit stuff going this way than you'd say towards you, but you're more likely to hit the stuff coming towards you the faster you're going into it. So the faster you're moving towards it, the more likely it is you hit the stuff going towards you. But you're still got, like I said, you got 4 dimensions, essentially 4 sub-dimensions versus just the one coming towards you. So you're got to be more likely to hit this, and this. So in a sense, that means the electron is constantly wobbling a lot, especially if it was in between two things. And so then you could argue that there's a lot more of this deflection stuff happening. That is, stuff is not coming out straight out of the electron. Instead, it's more likely to come out this way, this way, this way, that kind of stuff. And so then you could argue that this would still sort of work in the sense that the energy, the closer you bring the two things, the less likely you are to hit most of the energy. So most of the energy will miss you. Because you're going to start spraying it angularly more than you do straight at it. And so you could argue that as the electron moves back and forth this way, it would spray more stuff this way and this way and this way and this way. And so you can get it back to the point where it's sort of working in terms of getting rid of anything that's trapped between these two, would end up coming out in some direction that's not going to create a reflection. And that's really all you need to do. You don't need it to be specifically perpendicular. You don't need it to get rid of the energy in one direction. You just need it to get rid of it in either one of those two possible directions. Be back momentarily. Yeah, I think I'm back. So where was I? No, I'll read some more. Between just as if the electron wasn't there. The force bits will simply pass through the electron. You'd need a new explanation for why the protons can get so close to the nucleus. Yeah, well, that's sort of, like I said, the price you pay. So yeah, I guess the argument to be made is there's lots of ways to do this, and just because they've never thought about it in terms of a mechanical device that causes these things to happen, that nobody really knows or has thought about all the different ways you could create differences in pressure. Starting with this simple notion that we know dipoles exist, and so that would be how I guess I would say that I would argue that it just depends on the atomic scale what a dipole might look like. And part of this came up in another comment, because we really don't know the size of these things in terms of how charge manifests. Does it manifest out of mass, or does it manifest out of size? Profile. Because that's sort of important, especially, you see that with magnets, different size, little magnet strong, big magnet weak, big strong magnet, little strong magnets. You can have different kinds of relationships. So the idea would be is that the proton is something bigger than the electron. I mean, that's sort of an idea that's out there. And then we have, this is what we're working with, in a sense. Whoops, wrong color. You're starting with a neutron, and then you have a proton. So you're going to make a nucleus out of this substance. So here's your extra proton. So this is a proton, and this thing together is a neutron. We're just talking about what's the relationship between these things that make it possible for them, number one, to form a nucleus, a very tiny thing, And then the second argument is that somehow this relationship creates the opportunity to create something that can gain perpetual motion. That is, somehow it can create an engine of sorts where it somehow moves faster in one direction than the other direction. It does something imbalanced to fight against what would be argued as drag. This fact that if you're moving into a bunch of anything, especially stuff moving, but anything, you're moving into something, that you're going to hit more of it. The faster you're going, the more of it you're going to hit, in a sense. And somehow this overcomes that, and so a cosmic ray can get across the universe even though it's going through something. So it has to have an engine, a motor of sorts. But anyway, and the motor would be based on this fact that there's this relationship in terms of how magnets work. So the argument would be is that, as we have it now, the repulsive force is based on the fact that force gets trapped between things of common color, and that this can be a mitigator to that. It can change that. Well, the other point to make is that once this becomes a real dipole, once you put an electron on a proton, or very close, the idea would be is then you're going to have a force dynamic where the rules could be a little bit more, they change a little bit, in the sense that you could argue that this blue stuff ends up coming out of here at some more steep angle, like it is essentially bent through the process of the interaction between the two. And so, but the general idea is that you have this dipole where the blue energy all comes out of one end, the red energy all comes, well, in the case of the new diagram, actually it'll be exactly the opposite. Interestingly enough, is that this would be all red. Generally speaking, not all, but a higher percentage. Okay, and but let's say it is this kind of snowman scenario. Well, then you have, even though it's a dipole, it's an uneven dipole. One side is more than the other side just because of the density of the proton versus the electron. And so then you can create a scenario where this thing is maybe spinning, okay, or it's just wobbling. And so you can have sort of an understanding that there could be a wobble, like this electron swings back and forth this way, but it can't swing all the way. It can only go this so far till the energy ends up making the protons start moving further apart. So to say, the more that swung, the more this reflection happens. The further this one moves away, the closer it is, the more this one moves in. So I'm just saying, you come up with all kinds of mechanical circumstances where you could imagine that the force away, the repulsion force, is stronger than the force coming back in. All right, and so that would be your engine, because you have more velocity leaving, and you lose velocity as you come in. See, the more velocity this thing has in this direction, that is, the more likely you are to hit those arrows, and the more likely it is to slow down. So so it could leave quicker than it comes back, and something like that. So you could sort of get the idea that that could be your engine. It just made out of momentum. But who knows? I have to rethink the idea. But I'm just saying something as simple as that. And then the faster it's moving this way, the more it moves in this direction. And the slower this oscillates, the slower it moves in this direction. And that would give you some kind of way to, like we do, that would give you something to accelerate. So when you're accelerating, what's happening is the frequency of the neutrons swinging increases, and whichever way they're pointed, that is, whichever way is their swinging end, is the end in which they have velocity. So you're gain velocity by creating a higher frequency in the flipping of the neutron. And then this gets back to arguments about radioactive decay and all that kind of stuff, because all these neutrons are doing this in a nucleus. You know, they're all doing this pointing thing. Okay. And then you have to start talking about, well, how many of these neutrons can you point in one direction? And how well does the nucleus hold together when you're doing that? And, you know, so it brings up lots of other subjects. But I'm just saying this is all new ground, new territory, and so there's lots of room for finding some catch. And you're just trying to find the catch is that you have two things that behave oppositely in an inverse manner, and you're just seeing what's the consequences of that when you start throwing them together. And there's just so many ways to, there's so many geometric relationships, and then you can add to the geometry movement, because we know that movement has a consequence. Movement means that you're going to change the field you're interacting with. You're going to imbalance it just by moving. If you move closer to something and away from something, you're going to change its balance. And you know, so whatever. I get your point. We had a nice simple explanation for why protons are so close to each other, but it might be a tiny bit more complicated. You know, that might not be as simple, but we have a much simpler diagram of what's happening between electrons and protons. So the trade-off is you have a simpler diagram of electrons and protons, and you have a little more complex diagram of motion. All right. This made me realize I actually don't understand how the perpendicular reflection rule set can cause attraction between an electron and a proton with no other mass bits involved. Well, it seems kind of obvious to me. The three dimensions aren't going to bring in as much energy as the two leaving. So, well, anyway, imagine a red proton on the left side and a black electron on the right. Now let's think about what happens when the black force bits. The ones coming in from the left are never going to reach the electron now because the proton deflects them, fine. But half of the ones hitting the proton from the top and the half of the ones hitting it from the bottom are now just going to be redirected perpendicular into the electron. Right, the stuff coming in from the sides. So it seems to me the proton would fail to work as a shield. Going to 3D checkerboard doesn't change much. Well, it changes a lot in the sense that you have to recognize that you got 2 extra dimensions to get rid of the energy in, for one. And the other, I guess the other point I could make is it just depends on what direction you're going, which way is perpendicular. So, I mean, there was always some notion that there'd be a right-hand rule in here somewhere, you know, something that has to explain direction. So, I guess that was part of the diagram before, is that the idea would be is that it turns a particular way depending on what it's next to. So, especially the magnet, anything coming in perpendicular would always go out one way. So there wouldn't be any chance of it going another way if it's in a magnetic field. Alright. But half the ones hitting the proton on top of the bottom half going to be redirected perpendicular to electrons. So it seems to me that the proton would fail to work as a shield. So he's basically pointing out how the other idea had a flaw in it. The electron between the protons. So I guess I might as well draw that. I know I thought through that before, so there was some sort of explanation. I just don't remember it. So you have an electron. I guess I don't need to put him way over there. I can just draw closer. Proton, electron, proton. No, wrong. All right, and so the idea is that the red force goes out one of these directions, and in 3 dimensions, in or out. But the catch would be is that force is going to come in this way and this way and this way and this way, and occasionally, by odds, it's going to head for one of these. But the point is these has a profile is a tiny bit of the dimensionality that you have this whole radius here, and the whole radius here, these other two dimensions. So the odds of it going in the same direction as the proton on either side would be pretty thin. And you're guaranteed, when you're going out, you don't have to worry about hitting anything. You're just trying to get rid of the energy, so it doesn't matter which perpendicular direction it goes out. But when it comes in, it has to actually go one of these two perpendicular directions, and that the odds of that are lower than the odds of the stuff getting successfully out has much more opportunity to get successfully out than the stuff trying to hit the electron and the proton. That would be my argument. So yes, occasionally stuff will get it right, but it's still a lower percentage. It's like you gave away 80% and you're only going to get back 20%. So you're still way ahead. All right. 3D checkerboard. Okay. It doesn't change much. 1/4 up, 4th behind front directions are going to redirect the left click. Going to full 3D with all possible angles doesn't help either, because now there are even more perpendicular directions. But again, only one perpendicular direction of the whole range of possibilities, and so you're still talking about 1 out of 6 or something. It's not high odds. Same amount of force bits will hit the electron from the left either way. Yeah, I don't think so. But it's okay. It's a good enough argument. Like I said, I think if you go through it, you'll see that there's a difference between the likelihood of the perpendicular it ends up going being the perpendicular that's going to actually hit the proton. I can't think of an easy way to say it. See, all you're doing when you're trying to get rid of it, you're just throwing it anywhere. So it doesn't matter which way it goes. But for it to hit the electron coming in the other way, it matters which way it goes. I mean, it's only one tiny percentage of the whole pie, the whole 180 degrees. Only one part of that 180 degrees is going to hit the proton. And when you get rid of the energy, you're throwing it over the whole 180 degrees. You're not narrowed to some 30%. So the odds of you getting rid of something is a lot higher than the odds of you getting hit by something, because the profile of the proton is small enough still, and that's why they don't actually hit each other. Okay, it's because of that pressure. That's the whole point. The pressure coming from the outside is enough pressure to keep them from getting any closer than a certain distance, and that's as close as they can get. So the outside pressure is integral to the whole thing working in the first place, because you wouldn't, it has to stop someplace, or then you got the problem of the turning into dipoles, or colliding in some destructive way. I mean, the whole idea is these patterns can't mix. If these are patterns, they're just patterns in space, let's say, the patterns can't superimpose, because then they would, you'd lose your pattern. So the patterns there has to be some mechanism that keeps them at some distance. There's always a force they're being cushioned by. It's frictionless, let's just say. They never really hit each other. They just hit each other's change in the force around them. Okay. Probably a good enough. Alright, so Fireball says, if I was to relearn resonance. Yes, so that was in the last video. Just saying that all of these concepts, I just reiterate that they really don't teach them mechanically. They'll show you some experiments, but they really won't explain, like, okay, this is where this, energy is coming in, and this is, even with like magnets, they won't just explain, okay, understand, this is the field the magnet is. This is a piece of iron, so it's not a permanent magnet. Now this is a permanent magnet, and it's got an orientation it doesn't want to change. It's not going to change it easily, but this is really easy to change its magnetism. Just turn it in a different direction, and its magnetism is changed. And add another magnet, and this magnet, this piece is piece of iron isn't committed to being a magnet in one direction. So if you bring in another magnetic field, it's going to do its thing and change entirely its magnetic field, which is going to change the relationship between the three. Well, I'm just saying they don't explain it like that, like actually seeing the force or seeing charge working that way. They don't even explain charge as this idea that this thing is radiating its charge, that it is a force of charge, and that it's doing this inverse square thing where as the charge moves through space, it's separating in the sense that there's more distance. I mean, even with interferometers, they don't even concede this point that this is a huge part of what's taking place inside of an interferometer, right? They just pretend it's some kind of wave interference and that's as far as it goes. But a key thing that's actually physically happening, that they know is physically happening, is that as the light's traveling distance, it's diverging by this inverse square law, which means it's not only separating this way and this way, it's separating this way and this way. So it's separating in two dimensions. It's spreading. And that essentially gives you the power to measure distance, by just measuring the amount of a separation between the photons. It makes a ruler. So obviously the longer I make that path by using mirrors, the longer I make that divergence over distance, the more separation I get. Just like when they project the two-slit experiment, it's a magnifying glass, right? A slit or an aperture is automatically a lens, in the sense that you're causing more divergence of light, and the divergence is essentially enlarging, with distance. So the further away you put your piece of paper to watch your slit pattern, the more details you can see in the pattern, because you're enlarging everything as you do it. But what are you really enlarging? You're really enlarging the image of the surface. That's all you're making an image of the surface really big, in these locations. And that's what the multi-slit kind of tells you, is that you're just taking images of the surfaces. Each surface is making an image of a surface, and that is just ending up having a diameter, because of the fact that the surface is not just one tiny shred of something, it's a distance of something, and there's some variation in the angle you'll be deflected at, some slight variations. So within these rules of a certain angle, there's a certain amount of rules about how thick this thing will be. And they don't even talk about that kind of stuff. They don't talk about the actual width of these things and how you can change that by changing features of the experiment, change how deep the slit is, how thick the material is, what effect does it have on this projection of the image. So this is really a lens you're controlling. They really don't talk about it that way, but that's what you're doing. You're controlling a lens. You're making it fatter, or you're changing its function by changing these distances, and changing the light you're putting through it, just like a prism. The different wavelengths of light will be deflected at different angles, just like they are in a prism. It's in every way functioning like a lens, and it's just a hole. But it's doing the same thing, because the electrons that are forming the surface are providing the same function. The surface is here and the surface is here, and you could theoretically say the surface is a lens. The surface is like a bending surface. So and so you have more bending, going in on these angles, and that's what's causing the deflection of the light, just like a lens. Theoretically, right? I guess you could cut the middle out of a lens. If you had a traditional lens, just because of the way they work, you know, you could cut this part out, and it probably wouldn't have any effect, right? You could take the middle out of the lens, all right, because that light is supposed to go straight. Now the trick is, if you did that, then you'd end up with these surfaces again. So then you'd be creating lenses on the surface. You'd be creating lensing off the surfaces, and so that's what would screw it up. But in principle, this doesn't have to exist, because the light that's going through there isn't getting bent. You know, the part that's important is the part over here, you know, that's bending the light. So anyway, yeah, it's all, you know, food for thought and whatnot. So I think we'll do something. So maybe I'll play one of these videos. Not that guy. What's this one? Oh, that was the Hilster. That was just a waste of time. What's kind of funny, he got on the subject of his, you know, he does talk about his vegetarianism. Apparently he's not a vegan. I don't know. Or he said some vegans don't do it right, or some kind of horseshit. But anyway, so he's getting into the argument with these truthers. You know, the ones that they're often, the aggressive meat eaters are often people who don't give a shit about the environment either, in the sense that they're the climate change deniers. You know, so they're really people who just have some love affair with some kind of notion that human beings are this, you know, predatory. We're made to be Tyrannosauruses, really. You know, that's what we really were. You know, that's what our real heritage is. You know, we're real macho or something. It's just such garbage. And none of, I mean, it's just so easy to explain how that just doesn't logically make any sense. I mean, I've made the point, all this black stuff we put into the ground, right? The dinosaurs, the big plants, all of that, you know, the stuff that was happening 500 million years ago, was basically sinking carbon, aggressively sinking it, making it inert, okay? And then they'll say, oh, you know, carbon-based molecules are not very strong greenhouse gases. Well, so what? They don't have to be very strong. Doesn't matter. They are. And the real key, as I pointed out before, is as you raise the temperature of the atmosphere, it holds a lot more water. And that's the key to the whole. The water is a really good greenhouse molecule. So really what precipitates it going out of control is ending up with water in the atmosphere. Get a lot of water in the atmosphere and you're done. You're cooked. You're going to just spiral into getting everything into the atmosphere, because as it gets hotter and hotter, more and more molecules end up turning into gases, and you just end up with more and more molecules in the atmosphere doing more and more greenhousing. There's like nothing that's an anti-greenhouse molecule. You know, they all cause some greenhouse effect, and just some are worse than others. And obviously, because of its transparency, the water molecule is dangerous. All right. The fact that it makes little lenses, you know. But anyway, so I mean, it's kind of silly to sit there and deny that we haven't put all that carbon back in the atmosphere. It's just so obvious. We've taken a bunch of black stuff in the ground and shoved it into the atmosphere directly. To say that has no effect is just retarded. And then the vegetarian argument, well, I mean, the data on how you're healthier is just overwhelming, and they keep talking like, oh, the vegans are weak pussies and they're all almost dead and they're almost anemic, and it just isn't true. And the fact that they have less cancer and less of all this other stuff, these are just statistical facts you really can't deny. And they keep pretending that, no, it's really good. You could just sit here and just, you know, eat your fried lard and it has no consequence on your mortality, you know, when you're going to die. And it does. It's just stupid to argue otherwise. That there's, and you know, and then, but the real argument is, well, not the real argument. The real argument is, even if we were Tyrannosauruses, they're basically saying we couldn't civilize. So you could never civilize a Tyrannosaurus. So even though he knows, oh man, I am built really horrible, Okay, yeah, it's really terrible eating things alive, chomping. Oh, yeah, I don't want to do that. It's really cruel and stupid. So I'll figure out a way to do this without being an asshole. Just this idea of putting nutrients in my body. And the fact that we can make a milkshake and you can drink a milkshake a day and put everything you need in there is just a fact. The fact that you could do the Soylent Green thing, you could grind up dead people and make perfectly edible potato chips and eat them and live, is fine. Yes, that's true. So why are they pretending that we can't modify? Of course we can. Adapt to understanding better than a Tyrannosaurus, having more knowledge than a Tyrannosaurus. So again, it's just this idea that they think that nothing intelligent could ever overcome its biology, and that it couldn't behave decently or do anything gracefully. It's essentially what they're saying, that I can't do anything gracefully. I have to do everything like a pig in a slop. I can never play music on a piano. I can just bang on keys, because that's what I'm made to do. I'm made to just bang on keys. Just nonsense. But anyway, going back, and then so this whole justification comes from like somehow we just have to do it because that's what we were built to do. When we have absolutely there's no evidence that we have a single tool that would equip us as hunters. And so the only way we hunt is by making some instrument to do our hunting for us, to facilitate a trap or a snare or arrows or bullets and all this kind of stuff. We need to augment our physical tools. Obviously, our deep ancestors couldn't do that. They didn't have any augmentation. And then the second argument is there's no biological function to it. You're not going to derive any success out of it, because first, we can't digest raw meat, and you'd never be able to get to it, and it would be contaminated with a bunch of bacteria that were clearly not made to absorb. So none of it makes any sense, and the only thing that makes any meat eating possible is the tools, hunting tools, and fire. And without those two things, there's no way our ancestors could eat meat. And they certainly weren't eating carrion. They certainly weren't eating rotten corpses on the savannah. I mean, it's just an idiotic notion. The worst smelling thing to a human being is a rotting corpse. I mean, it's this offensive, horrid smell. I mean, there's absolutely no chance that we chowed down on decomposing, rotting flesh. I mean, it's just retarded to make the argument that somehow we were eating roadkill. It's the most unappetizing thing you could imagine, unless you drag it over to a fire. So this is just an idiotic. It's just they're so desperate. But I mean, it was just kind of funny to watch, just because they're all saying, I'm going to unsub and I'm blah, 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 blah. But they just can't take it. Because it's, and I would argue that, David doesn't really argue his points very effectively, in the sense that he just basically does what everybody else does and says, I have this and I have statistics, instead of just making the logical argument that, what do you think? You really think that 2 million years ago, before humans had fire, that they were realistically chasing down other mammals, chewing off their flesh with their teeth, their fur, to eat something totally uninteresting to our taste buds, raw flesh, that they can't chew with their crappy flat teeth? Let's understand, I mean, baboons are mostly vegetarian. Huge, giant teeth. Yeah, teeth for fighting. Teeth for a different purpose. Okay, but their back teeth aren't flesh-ripping teeth. Anyway, I mean, just this, then you go into the other biology, which has to do with the length of our digestive tract, all of this stuff, that there's no way we were designed to eat meat, especially raw meat. Just idiotic. Alright, anyway, I'm just throwing that in. I mean, it is funny to just watch the panic, and it's just as, it's just a truther world. I mean, people have their notions, and they just will not be logically, they are impervious to logic, just clearly. Mostly. Entirely. Alright, so before I play this, maybe I'll take a break. Have some smoke. Well, I can smoke while I watch it. Yeah. well, we'll see. Yeah, I'm back. Just thinking, yeah, I could end up, doing preface drawings and use up all my time. So we'll just play some of this and see if there's any necessary. It probably will be necessary to explain some of these things. But anyway, let's jump to some portion here where this is. So this is like a play. So done by PBS. I don't know why PBS shows aren't free everywhere, but whatever.
Thank you.
No, thank you. So it's this Brian Greene guy who's all this animation, all this, Barney the dinosaur of science, I mean, really bad. All this emotional bullshit.
April 17th, 1955, Albert Einstein experienced a painful tightening in his chest. He was admitted.
Okay, so they're doing the end first. He had an aneurysm and chose not to attempt to have it sewn up. So I guess he figured he was done anyway. Tired of it all, I guess. I don't know, I wouldn't bother with hospitals and all that nonsense either, but that's me.
I can still remember, or at least I believe I can remember, that this experience made a...
Okay, so this is, they have this guy portraying Einstein, so they didn't even try to make him look like Einstein. It's kind of funny. But they do the accent stuff, like somehow the accents are important, but don't have to look like, they have women reading male parts, so. But with accents for whatever reason. But anyway. So this, there's all these little stories, and some of them, I guess, Einstein told, about what inspired Einstein to think about the universe. I mean, about 1 billion of us has done this, right? I mean, some people don't bother, okay? Some people just don't bother. They're just worried about soft kitty, blah, blah, blah in life, and they don't really do this contemplation thing. They don't have a bug sitting in their hand and think about, look at that thing. It's like a little dinosaur, and it's, look at what's it doing? Why is it doing it? How to get here? How, some people do think, some people don't. So I don't, this is just this over dramatization, as if Einstein was the first person who was curious. I don't think so.
A profound impression on me. Something deeply hidden had to be behind things.
The boy could feel the power of...
Yeah, it's just, everyone, like I said, it's only like 1 billion, 1 in 10 or something. I mean, it's not like it's that dramatic an event for somebody to be curious. But whatever, just way overdone bullshit.
Parents, I came to a deep religiousness, which, however, abruptly ended at the age of 12.
So it took him to the age of 12 to figure out God was a dumb idea. It's a retarded story. It doesn't make any sense at all. Where did God come from? Who made him? He sat around forever and came up with the idea of buttholes. I mean, come on. Shit. Right. I mean, there's no logical continuity to that story at all. So the fact that it took him 12 years to figure out that was horse shit. I mean, I just never could do it with any, this whole religion thing. Just it always seemed like, oh, I'm not allowed to have a bad attitude, so I have to believe in you. Oh, okay, I'm believing in you. Yeah, that was his. I couldn't get any more sincere than that. Can you hear me believing in you thing? Yeah.
Through the reading of popular scientific books, I soon realized that much in the stories of the Bible
This is a different guy now. Yeah, it took him 12 years to figure out much of the Bible is bullshit. Oh, funny. The whole thing is just doesn't have anything to do with there's not a, they don't have like a good phrase even for a penis. I mean, that was the turnoff for me. They what this should be called the story of penis, because what else is important? Especially at that age, there's nothing else that was really important. So how could this Bible have anything to do with reality when it didn't seem to care at all about the penis?
Kind of makes me wonder what he'd think about the Common Core. Head of the physics department at the Zurich Polytechnic was Heinrich Weber.
So he ended up in a dispute with him eventually.
And during Einstein's first couple of years...
Alright, this is kind of boring part, so we won't bother with well, this.
for his final diploma requirement.
Right, so Einstein was smart, but he pissed off his professors, and he wasn't good at doing playing the game the way you have to play it. So he didn't schmooze and protect his future well enough. So he ended up in a patent office, okay, through connections and kind of lucky and blah, 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 blah.
A busy and exciting time as the full potential of technology that harnesses electricity is beginning to emerge.
Well, yeah, a lot of things are emerging. Automobiles, airplanes, lots of stuff happening. Yeah, it's very interesting times.
And one fascination sweeping across Europe and reflected in the patent applications has to do with the synchronization of clocks. You see, in the old days, if a clock in Berlin and another in Bern were somewhat out of
Okay, so this is terribly uninteresting. So look, the fact is that, Einstein's father had a company. There's always something going on here that's irritating. I have to do this menu thing. Menu, okay. His father was doing an electric light bulb thing, as Einstein was growing up and they had generators. And so, he was exposed to all this stuff, in a way that most people weren't.
sync. No one much cared, right? Communication was just too slow for it to matter.
Just too
Without
slow.
saying hello.
This is like some kind of William Shatner of science. It was just too slow.
Thank you. I have completely solved the problem.
This wasn't much of a story either. He didn't solve anything, obviously. His Eureka was kind of...
Solved. Perhaps I really should say puzzle shifted, because the new puzzle is, how could light speed behave?
How could light speed behave so bizarrely? How could that happen? Spock! What's the answer, Spock? Spock!
In such a crazy way.
In such a
Well,
crazy way.
think about speed for a moment. What is it? It's a measure of how far you go compared to how long it takes you to get there.
Spock!
So it's a measure of
Speed!
distance,
It's amazing!
space divided by duration, time.
Time and
So when
space
Einstein said that
and
the speed of light is constant,
penises.
the speed of light behaves weirdly, he was actually saying that space and time behave weirdly.
Yes, but time doesn't really behave weirdly. It's so fucking consistent and reliable everywhere we look. How can it be that it isn't regular when it is so fucking regular?
That's what set off the storm in his mind. He realized that space and time execute a fluid.
So let's understand, what space is executing is the inverse square law. Okay, that's what it's executing. So it's just this simple idea. If you thought about it like it was a light bulb, Earth is a light bulb, or it's a reflective surface, it really just doesn't matter. And that the light comes from little tiny places, and from each place the light can come out in any one of these directions, in every single little location. And well, anyway, and the idea is that the surface is essentially creating a bunch of light that is diverging, that is moving with distance away from each other. So the photons from the light bulb, they start in one tiny place and then they're going to a big place, this big giant circle. So they're leaving this little tiny circle and they're going to this big giant circle. And the fact is if you had to spread, whatever, mustard, you could have thick mustard here, but you can only have thin mustard here. And it's going both ways. The bread goes both ways, And that's the inverse square law. And that's all there is. All right, so there's this r squaredness to space that you can understand that. Okay, just by these radial lines, they get further apart the further away you go. That's the concept. And somehow they're saying time now is doing that. Somehow time is two-dimensional. It's moving in two dimensions. It's moving this way and it's spreading this way and this way. Why would time do that? It doesn't make any logical sense.
Choreography in which they adjust themselves in tandem to keep the speed of light fixed. And that's what makes this all such a big deal. I mean,
It makes it a big deal that the speed of light is the speed of light. It's how much distance you cover in a certain amount of what we're going to call time. And that you can't cover that distance no matter what little frame you're in, no matter what poop you're doing. It doesn't matter. It's always the same in the universe. So again, this whole, my frame says I'm time dilated. Well, it doesn't matter because the universe isn't time dilated. The universe went about its business by the same rules it's always had. So nothing really changed. You did move as fast as the speed of light. You did keep up with it. All right? Because it's evidenced in the fact that the rest of the universe got 1 billion years older.
no one would really care that much about some esoteric, strange feature of the speed of light. Strange.
It's not a feature of the speed of light, it's a feature of perception. You have to understand something to understand it. So if I don't tell you there's a third dimension, I mean, I could draw this and you see those lines, you say, well, that's only twice as distance as this distance. It's only twice as long here. So what's the problem? It's only twice as much force there. Well, that's because I didn't draw the third dimension, right? So you don't see it unless you know it's there. And that's the problem with this whole, let's think about time dilation. And we always have to do it in these abstract ways that, you know, thinking of bent space. Bent space is a metaphor for something that's obviously a three-dimensional convergence. It's obviously behaving just like a light bulb. You could explain Einstein's anti-divergence, that's what they call it, an anti-divergence. Okay. But just talking about light bulbs. Because they do exactly the same thing.
Features of space, strange features of time. Yeah, that matters. That speaks to strange features of
Strange. But you have to emphasize it's all so strange and mysterious. You know, it's a mechanical universe. There's a cause to the effect.
reality. And Einstein was able to work out those strange features of reality, and he did it with nothing more than high school algebra. He found that if you had
Yes, and he got the wrong answers, some of them. I mean, his first prediction of, his theory the first time he published it was still using. So it might be in this actually, this part of it, might be. They were going to do the eclipse like in 1912, because there was an eclipse then. And it happened that the whole war thing happened, and so the war ruined doing the eclipse experiment. But the truth was that if they had done it, Einstein's number was still Newton's number. So, wonder what the result. I wonder if they would have found it. See, that would have been funny, right? They found it with the wrong number.
have two clocks, one stationary and the other moving, that time will elapse slower on the moving clock compared to the stationary one.
So time will move slower. So again, it's just this whole idea that they're not explaining that, no, the clock could just be broken. The clock counts time wrong. Okay? You broke the clock. The clock's not working the same way because the atoms aren't in the same positions. And so the clock isn't keeping time right. And it's so easy to break clocks. All kinds of clocks can be broken. The electronic clocks, you make them hot or cold, they don't keep time as well. Lots of things, lots of ways to break clocks. And that's all you're doing. We're a clock. We have mechanisms that are on a timed interval. Our atoms are clocks. The rotations or movements of the objects is a clock. Heat changes clocks, you can say. How fast water evaporates. So lots of things will change. You increase temperature. You agitate the system.
And it's not just that the clock's inner mechanism is running slow.
It's not just that. You should say, we claim, okay? It's not that the clock is innerly being affected, that it's a cause and effect. The clock is being broken by the velocity. He doesn't say it overtly. He says it's not just that. No. It either is that or it's something else. But you can't have it both ways.
Einstein found that time itself is slowing down.
Whatever time itself is, right? And it's not time itself that's slowing down. The light still moves exactly the same speed, and all we're saying is that you perceive, okay, there's a slight difference in your speed with the speed of light, and so the light is still gaining on you with distance. And all they're saying is that you're perceiving that gain poorly. Okay, I mean, and the fact is the rest of the universe is going on about its business. So the rest of the universe, the speed of light was the same. You'll move through the universe. You have to be going very fast, so you're flying past things. I mean, just zooming right past them at incredible speed. Right? I mean, it is 8 minutes to the sun. It is, it's a fast speed, but it's not. But I'm just saying, there's nothing here but your perception. There's no physical. It's not a fact that if you're going as fast as light, that the two objects aren't flying through the universe at insane speed. Of course they are, and you're just measuring the difference, how much one's gaining on the other, and saying that this object doesn't perceive this gain thing happening at regular speed. It perceives it at this super slow metabolism speed. Where one blink of your eye is 1,000,000 years.
So all processes of motion slow, from aging to thinking to twerking. Completing the dance. Einstein also found that space behaves weirdly. If you have a couple taxi cabs, one stationary and another that rushes by at high speed, you'll find that the height and the depth of the speeding taxi cab unchanged, but its length in the direction of motion will be shrunken. And
so again, this is the part that doesn't make much sense to the gravitational wave theory, but somehow they're contracting in one dimension and expanding in the other dimension, so there's no consistency to this mush.
Trying to jump into that squeezed taxi cab, you'd think I'd crave some legroom, but actually, relative to my new perspective, it's the rest of the world that's rushing by me, so the interior of the taxi appears ordinary.
That's not ordinary. It made you really small. Didn't even recognize that fact. But anyway, so again, all this about perception, what you're going to perceive, as if we know that we can take a piece of our physical matter and move it to these insane speeds and have much hope that it stays in one piece, when there's no evidence of that.
And it's the outside world that undergoes all these wondrous...
Matter obviously does not acquire these speeds in nature, except for the cosmic rays. I don't know what their maximum speed is. There's no examples of matter getting anywhere near the speed of light.
Distortions. At everyday speeds, these effects are too small for us to notice. But if we routinely traveled near the speed of light, that's fast enough to go around the entire Earth 7 times in a single second. At those speeds, these effects, they would be obvious. We'd experience them all the time.
Well, these effects, though, have nothing to do with what's happening, and it certainly doesn't have to do with the photons reflecting off anything. So the fact is, you wouldn't see any of this. You wouldn't perceive it in any way, because you'd have nothing to perceive it with. You'd have no photons to interact with. You'd have no vision. You'd have no radar. You'd have no way of seeing the rest of the universe, because you would be negating your absorption of it. I mean, just, if you're going the speed of light and light's coming off objects, you're not going to receive enough information to ever see anything. You're not going to be able to absorb a whole photon. Photon might be this long. You're going so fast, you'll barely interact with the photon in the terms of its frequency. You would never be able to detect the frequency of a light ray. You'll never be able to do any of that stuff. So this is nice imaginary gameplay, but it has nothing to do with real physics. Real physics won't let you do any of this stuff. Now, maybe I'll save the rest for next time. Do a piece at a time. The interesting part to get to is the whole Eddington hype, right? The Eddington experiment was crap. Einstein's number. I'm still not exactly sure why he did it. So his first relativity theory said whatever it is, 0.83 or something, arc seconds of deflection, and then in 1915 or whatever, he increased it to 1.27 or whatever the hell it was, or 3 something or other. It's like a doubling. It is a doubling, but I obviously don't have the right numbers here. Maybe this was 7.3. Still would be too much. But anyway, it's almost a doubling. And why? Why? You just asked the question, why are photons, unlike all other matter, so now photons are in a special category. See, this number, Newton's number, would apply to an Earth going through the same gravitational space, and we're really talking about by the place this is. This is 1 solar radius, okay, just a radius from the sun. So that's where you have this tiny. It's already a tiny amount of deflection you have when you're just 1/2 diameter, and that's essentially what they decide is the corona. But we know the corona extends much further than that. It just gets weaker. That's all. So there's lots of room for scatter, of course. But anyway, let's get beyond that. I mean, you can't see things here and here and here and here next to the sun, just because the fact is there is a bunch of crap there, and the light's going to get blocked or scattered. It's certainly going to be less light you're going to get through. And so you have to pick something that's further away from the sun to be able to see if it's getting lensed. Which again makes part of this whole thing nonsense, because they're saying they're seeing things. Well, Eddington's experiment, they're speculating that you could see something behind the sun. Well, we really can't, because the corona is really in the way. But anyway, there's not enough deflection. And again, let's understand, gravity gets weaker as it goes further away, which is the opposite of a regular lens. A regular lens does more bending on the edges and less bending in the middle. And this lens does exactly the opposite. It does more bending the closer you get to the middle, less bending further away. So the whole thing doesn't make much sense. But why the doubling? So if the Earth went right through this area, it would be bent, whatever it is, 0.83 or something. The sun, an elephant, doesn't matter. Doesn't matter what your mass is. Mass is irrelevant. Only thing that matters is your velocity. So if you move an elephant the speed of light past the sun at this point, this is how much deflection you're going to get. So why is a photon now twice as much? Something that we have, number one, no evidence that photons are moved by forces. We can't move it with magnetism. We can't move it with any other force we know of. But somehow it does this. And this is a kind of a bold statement, a doubling for no good reason. Lots of things, lots of elements to this, and the evidence is so bad. In the sense, the experimental evidence, they won't even show you. They won't show you the Eddington pictures. They won't show you anything, because it's crap as evidence. Crap. All right, anyway. I've made all these points in the past, but I mean, if somebody can understand, I mean, why the doubling? Why would the photon need to be bent twice as much as any other material object? Why this special case? The fact that it's bent is one question. The fact that it's bent twice as much, why? What's so special about photons that they bend twice as much as electrons or protons or neutrons or atoms or elephants? Somebody know the answer? If I knew it, I don't know it anymore. I don't remember it, but there's some catch to it. But I mean, it's this whole idea of turning time into a two-dimensional object, I think, is the reason. He's got to do the inverse square thing to it. And it might have to do with Lorentz contraction. You can't Lorentz contract it or transform it or whatever it's called. I mean, you can't do this idiotic chart for time dilation. You can't do this, no, very little time dilation, and just all the time dilations here at the end. You can't do that, without an inverse square rule. So they're just taking, so the profile for gravity, okay, would be exactly the opposite profile, right? Well, that's not the way to draw it. This is the way to draw it. So, gravity very strong, lots of change, and less change for infinity. So they turned time into a gravitational. They made a gravitational argument, as if time is separating in two dimensions. As if time was doing this inverse square thing. It's not. I withdrew the square thing, but it's not doing that. It's not spreading in two dimensions. Why is time spreading in two dimensions? It doesn't make any sense. I'm sorry. It just doesn't make any sense. Stop defending something that's so poorly. It's a bad theory, like God, and it's really badly evidenced. So let it go.